Right now, more than 13 billion miles from where you are sitting, a machine smaller than a small car is moving through a region of space that has no name on any map you have ever seen, carrying a signal toward Earth that will take more than 19 hours just to arrive. It launched before smartphones, before the internet, before most of the engineers currently keeping it alive were even born. It was supposed to die in 1981. It did not die. Instead, it kept going, and in doing so, it did something no other machine built by human hands has ever done. It left the solar system entirely, and unlike its more famous twin, it did it with an instrument still switched on that let it actually measure what was happening at the exact moment it happened. This is the story of Voyager 2, the quieter of the two Voyager spacecraft, the one almost nobody talks about compared to its sibling, and the one that just gave scientists a piece of data so strange that some are still struggling to explain it. And here's the part that makes this story matter right now, in this exact month, rather than as some dusty piece of space history. Because in the last few days, NASA engineers pulled off something they were not fully sure would work. A maneuver so drastic they nicknamed it after the beginning of the universe itself, and it just bought this aging, dying spacecraft an entire extra year of life at the edge of everything we know. Stay with me, because the full story connects a 1977 rocket launch, a boundary in space that should not exist the way it does, a legendary scientist who spent 50 years listening to this spacecraft and did not live to see how it keeps unfolding, and a countdown ticking right now toward a silence nobody can stop. Subscribe now if that sounds like your kind of story, because we are only getting started, and what happens with Voyager 2 in the coming months is going to matter more than most people currently realize. Let's go back to where this begins, because the origin of Voyager 2 is stranger than people remember, and it starts with a coincidence of orbital mechanics that will not happen again for another century and a half. In the late 1960s, a graduate student at NASA's Jet Propulsion Laboratory noticed something almost nobody else had spotted. Once every 176 years, the four giant outer planets of our solar system, Jupiter, Saturn, Uranus, and Neptune, line up in a way that lets a single spacecraft use the gravity of each planet to slingshot toward the next one, saving decades of travel time and fuel that no rocket of that era could otherwise provide. That alignment was happening in the late 1970s. NASA had a window, and if they missed it, humanity would not get another shot at visiting all four giant planets with one mission until sometime in the 22nd century. Two spacecraft were built to take advantage of it. Voyager 2 lifted off first, launched on August 20th, 1977 from Cape Canaveral. 16 days before its twin, Voyager 1, followed it into space. The numbering seems backwards until you understand the plan behind it. Voyager 1 was placed on a faster, more direct trajectory designed to reach Jupiter and Saturn sooner, and then use Saturn's massive moon titan to bend its path up and out of the solar system entirely, sacrificing any chance of reaching Uranus or Neptune in exchange for speed. Voyager 2 was given the longer, more ambitious route, threading a path toward two worlds that no spacecraft in history had ever visited or has visited since. The mission's official goal at launch was almost absurdly modest. NASA budgeted for a 5-year mission. The plan was Jupiter, then Saturn, then a graceful retirement sometime around 1981. Nobody wrote explore the edge of the solar system into the original mission plan because nobody at the time knew for certain that edge could even be reached, or precisely what it would look like when a spacecraft got there. What happened instead is one of the most extraordinary extended careers of any machine humans have ever built. Voyager 2 reached Jupiter in July 1979, sending back images of swirling storms and discovering a previously unknown 14th moon in the process. It reached Saturn in August 1981, mapping ring structures in a level of detail no Earth-based telescope could ever achieve. Then, instead of ending, it kept going, because the alignment was still there and the spacecraft was still healthy, and NASA extended the mission toward Uranus. In January 1986, Voyager 2 became the only spacecraft in human history to fly past Uranus, discovering 11 previously unknown moons and 2 new rings, and measuring something genuinely bizarre about the planet itself. A magnetic field tilted a staggering 59 degrees away from its axis of rotation, so far offset from the planet's center that it still challenges the models scientists use to explain how planetary magnetic fields form. 3 years later, in August 1989, Voyager 2 reached Neptune, the last planetary encounter in the mission's history, and delivered a final wave of discoveries before its cameras were switched off for good. It found the Great Dark Spot, an Earth-sized storm churning through Neptune's atmosphere. It measured wind speeds above 1,300 miles per hour, the fastest sustained winds ever recorded anywhere in the solar system. It discovered 6 new moons, including one called Proteus, large enough that many scientists were surprised it had not already been spotted from Earth. And it studied Neptune's largest moon, Triton, closely enough to find active geysers of nitrogen gas erupting from its surface and to determine that Triton was almost certainly not born there at all, but was instead a captured world from the Kuiper Belt, pulled into orbit by Neptune's gravity sometime in the ancient past. After Neptune, the cameras went dark permanently. There was nothing left to photograph. Mission planners could have ended things there with a mission that had already dramatically exceeded every expectation. Instead, they turned the spacecraft outward, toward the edge of everything the sun's influence touches, and kept listening. This is where most people's knowledge of the Voyager mission simply stops, because the headlines belong almost entirely to Voyager 1 from here on. Voyager 1 gets the fame because it got there first. In August 2012, it became the first human-made object to cross into interstellar space, the region beyond the heliosphere, that enormous bubble inflated by the constant outward pressure of the sun's solar wind, containing every planet, every moon, every asteroid, and every living thing we know of. The edge of that bubble is called the heliopause, and it is, in the most literal sense available to us, the actual physical boundary of our solar system. Cross it, and you are no longer in the sun's neighborhood. You are in the space between stars. But here's the detail that almost nobody outside the mission itself talks about, and it is what makes Voyager 2's story genuinely more important scientifically than the more famous crossing that came before it. Voyager 1's plasma science instrument, the device designed to directly measure the temperature, density, and flow of the charged particles making up both the solar wind and the interstellar medium, had already failed. It stopped working in 1980, decades before Voyager 1 ever reached the heliopause. That means when Voyager 1 made its historic crossing in 2012, the instrument needed to understand what that crossing actually looked like, had been silent for 32 years. Scientists could infer things indirectly, from the cosmic ray detector, from the magnetometer, but they could not directly measure the plasma itself, the actual substance of the boundary Voyager 1 was passing through. There was a hole in the data, no way to fill it. Voyager 2, taking its longer route through all 4 planets, did not cross the heliopause until 6 years later, on November 5th, 2018, at a distance of roughly 119.7 astronomical units from the Sun, just under 11 billion miles out. But Voyager 2's plasma instrument was still alive, still working, still measuring. For the first time in human history, a spacecraft crossed the true edge of the solar system while carrying a functioning device capable of directly recording what the plasma on both sides of that boundary actually looked like in real time as the crossing happened. What that instrument recorded turned out to be one of the most important scientific data sets ever collected from beyond Earth, and the results, published as 5 separate peer-reviewed papers in the journal Nature Astronomy in November 2019, forced scientists to reconsider assumptions that had gone essentially unchallenged for decades. The first surprise involved the sheer thickness of the boundary itself. Before Voyager 2's crossing, the working assumption among heliophysicists was that the heliopause would be a relatively narrow, sharply defined line, a transition zone perhaps a few 100,000 kilometers wide, where the hot, fast-moving solar wind gave way cleanly to the colder, denser plasma of interstellar space. What Voyager 2 actually measured was something stranger. Just outside the heliopause, in territory that was supposed to already be interstellar space, the instruments detected a distinct transitional layer roughly 100 million miles wide, filled with interstellar particles pushing inward through the boundary like roots, forcing their way through cracks in rock. It was not a clean wall at all. It was closer to a coastline, with material washing across the border in both directions, mixing in ways earlier models never accounted for. The second surprise concerned temperature and density together, and this is where Voyager 2's working plasma instrument mattered most. Because for the first time, scientists had an actual number instead of a theoretical estimate. The plasma inside the heliosphere, energized by the sun, registered at tens of millions of degrees. The plasma, just outside the heliopause in true interstellar space, came in at a directly measured temperature between 30,000 and 50,000 degrees Kelvin, hot by ordinary standards, but dramatically cooler than the environment just inside the boundary, and roughly half of what earlier theoretical estimates had predicted. At the same time, the density of that interstellar plasma turned out to be more than 40 times greater than the density of the solar wind at the heliopause, confirming that the space between stars is thicker and more substantial than the thin bubble our solar system sits inside. Stimatios Krimigis, a senior scientist on the mission at the Johns Hopkins Applied Physics Laboratory, pointed out something else that genuinely stunned the team. Voyager 1 crossed the heliopause near a period of high solar activity, called solar maximum. Voyager 2 crossed near the opposite extreme, solar minimum, when the sun's output was much weaker. Existing models predicted the heliosphere should expand and contract with the strength of the sun's activity, meaning the 2 spacecraft should have found the boundary at noticeably different distances depending on when they crossed. Instead, both found the edge at almost exactly the same distance, Voyager 1 at 121.6 astronomical units and Voyager 2 at 119 astronomical units. Krimigis said it plainly, "We don't understand why that is." Coming from a scientist who had spent decades studying this exact data, that admission was a signal that something fundamental about how the sun's activity relates to the size of its own protective bubble does not work the way the textbooks describe. The third finding, the one Voyager project scientist Ed Stone at the time called the most remarkable result of the entire crossing, was that the heliopause leaks, not metaphorically, literally. Particles cross that boundary in both directions, constantly, in a process nobody had fully appreciated before these two spacecraft provided direct measurements from two different points on the boundary, at two different times, approaching from two different directions. Voyager detected interstellar material pushing inward before it fully crossed. Voyager 2, approaching from a different angle entirely, detected a trickle of low-energy solar particles leaking outward into interstellar space before it had even reached the heliopause. Two different mechanisms, observed independently, both pointing to the same underlying truth. The edge of our solar system is not a sealed wall separating us cleanly from the rest of the galaxy. It behaves more like a permeable membrane, a living boundary where material and energy are constantly exchanged between our home and the vast interstellar ocean surrounding it. Stone summarized it in words worth sitting with. The Voyager probes are showing us how our sun interacts with the stuff that fills most of the space between stars in the Milky Way. Not where the sun ends, how the sun interacts with what lies beyond it. That is a fundamentally different picture of our place in the galaxy than the one most people grew up with. Before we go further into what is happening with this spacecraft in 2026, I want to pause on something that connects all of this together. Because it is easy to talk about instruments and data points and forget that behind every one of those numbers was a specific human being who spent an entire career listening to this machine. Ed Stone was 36 years old in 1962 when NASA handed him the position of chief scientist for the Voyager mission, years before either spacecraft had even been built. He held that position for the next 50 years, guiding the mission through its planetary flybys, through the long, silent decades of the interstellar cruise, through both heliopause crossings, and through every triumph and setback in between. He retired from the role in 2022. He died on June 9, 2024, at the age of 88, having spent more than half a century of his life connected to two machines that were still, at the moment of his death, actively transmitting data back from beyond the edge of the world he had spent his career studying. Colleagues described him as a trailblazer who dared mighty things in space, whose steady leadership held together one of the most ambitious and longest-running scientific missions humanity has ever attempted. The mission's own social media account, written for years in the voice of the spacecraft itself, marked his passing with a line worth repeating: "Thank you for opening the door to our celestial exploration. Your legacy lives on beyond the heliosphere." And it genuinely does. The instruments Ed Stone spent 50 years interpreting are still running right now, still being read by the team he trained and left behind, carrying forward a relationship with two machines that has now outlived the man who understood them longer than anyone alive. If a story like this is the kind of thing you want more of, take a second to hit that like button right now, because it genuinely helps this kind of careful, fact-checked space story reach more people who would actually appreciate hearing it properly explained instead of buried under exaggerated headlines. Now let's talk about what is actually happening to Voyager 2 right now, in this exact stretch of 2026, because the mission is entering what may be its final and most dramatic chapter. And the timeline is far tighter than most casual observers realize. Every system on the Voyager spacecraft runs on power from 3 radioisotope thermoelectric generators, sealed containers of plutonium-238 that produce heat as the plutonium decays, heat converted directly into electricity. At launch in 1977, those generators produced approximately 470 watts of power, enough to run all 10 of the original scientific instruments, plus every heater, transmitter, and support system the spacecraft carried. Because plutonium-238 has a half-life of roughly 87. 74 years, the power output declines predictably and permanently, losing around 4 watts every single year with no way to reverse or refuel it. Today, after nearly 49 years of continuous operation, both Voyager spacecraft are running on roughly 2/3 of their original power budget, and every year that fraction gets smaller. Mission engineers have spent more than a decade managing an increasingly brutal set of trade-offs, switching off instruments one at a time, choosing which pieces of ongoing science to sacrifice in order to keep the transmitter and the heaters that prevent the electronics from freezing permanently alive for as long as possible. Since 2024 alone, the dwindling power supply has already forced the mission to permanently shut down 2 more science instruments on each spacecraft. Voyager 2's plasma science instrument, the very device that made the historic 2018 heliopause measurements possible, the instrument Voyager 1 lost back in 1980, was itself finally switched off in 2024, its scientific purpose largely fulfilled once the spacecraft had moved well beyond the boundary it was built to study. Without intervention, mission engineers calculated that Voyager 2 would have been forced to shut down yet another one of its 3 remaining instruments before the end of 2026. Losing an instrument like that is not a small administrative decision. Every instrument switched off represents a category of scientific questions that will simply never be answered, because there is no way to send a new spacecraft that far in any relevant time frame, and no way to ever switch an instrument back on once its shutdown is finalized. So instead of accepting that loss, a team of engineers at NASA's Jet Propulsion Laboratory spent roughly a full year working on an alternative, a technique so aggressive and so unlike anything attempted before on either spacecraft that they gave it a name borrowed from the origin of the universe itself. They called it the Big Bang. The idea was to completely restructure how electrical power flows through Voyager 2's remaining systems all at once, powering down a group of devices and simultaneously swapping them for lower power alternatives capable of doing the same essential job for less electricity, all while making certain the electronics stayed warm enough to avoid freezing permanently in the extreme cold of interstellar space. The reason for doing it all simultaneously rather than gradually comes down to risk. Any transitional moment during a power reconfiguration like this creates an unstable intermediate state, and those unstable moments are exactly the kind of thing that can trigger the spacecraft's automated fault protection systems, mechanisms built in decades ago that will begin shutting components down on their own if they detect power draw exceeding what the generators can currently supply. Skip through that dangerous transition quickly, and you reduce the window for something to go wrong. Linger in it, and you multiply the risk. Every command involved in this procedure had to travel across a communication link stretching more than 19 hours one way, meaning a single exchange, a command sent up and a confirmation sent back down, cost the team the better part of 2 full days, with no opportunity to intervene in real time if something unexpected happened mid-procedure. This was closer to remote surgery performed on a patient nearly 50 years old, using tools designed decades before the surgeon was born, with every decision locked in almost 2 days before its outcome could even be confirmed. In the first days of August 2026, NASA confirmed that the Big Bang procedure on Voyager 2 had succeeded. According to the mission team, the results matched their predictions so closely that engineers completed the entire reconfiguration exactly as planned without needing to alter their approach mid-procedure, a level of precision that is genuinely remarkable, given the distance and delay involved. Kareem Badaruddin, one of the engineers who led the effort, described it afterward as a team effort representing the culmination of a full year of work, with almost every single member of the mission team contributing. The result of that year of preparation is that Voyager 2's 3 remaining instruments, its magnetometer, its plasma wave subsystem, and its cosmic ray subsystem, now have enough power to keep running for at least another full year longer than they would have otherwise. That may not sound like a dramatic headline number on its own, but understand what it represents. It means more months of continuous, real-time measurement from the only functioning scientific outpost humanity has sitting physically inside interstellar space. It means more data feeding into questions about the shape of the heliosphere, the interstellar magnetic field, and the strange leaky boundary Voyager 2 helped discover in 2018. And it means the mission team bought themselves something almost as valuable as electricity itself, time to plan the next move, because the Big Bang was never meant to stop with Voyager 2. It was designed from the beginning as a proof of concept, a live test on the spacecraft slightly closer to home and better supplied with power, so that if anything went wrong, the consequences would be marginally less catastrophic than attempting the same untested procedure on its more distant twin first. Voyager 1 needs this intervention more urgently than Voyager 2 does right now, and the story of why reveals just how unforgiving this stretch of the mission has become. In February 2026, during a routine maneuver that rolled the spacecraft to point an instrument at a different target, Voyager 1's onboard systems detected a sudden, unexpected drop in available power, a fault that forced engineers on the ground into an emergency response despite the crushing communication delay working against them at every step. Acting as quickly as a system with a round trip well beyond a full day possibly allows, the team made the difficult call to permanently switch off Voyager 1's low-energy charged particle instrument on April 17, 2026, an instrument that had been continuously measuring charged particles from both the solar system and the wider galaxy since before most of the current engineering team was born. That decision left Voyager 1 running on just 2 active science instruments, noticeably behind Voyager 2's remaining 3. With the Big Bang now confirmed successful on Voyager 2, engineers are planning to attempt the same reconfiguration on Voyager 1 in the coming months, hoping not only to stabilize its reduced instrument set, but potentially to bring the low-energy charge particle instrument back online. Nothing about that outcome is guaranteed. Voyager 1 sits farther from Earth, meaning its own communication delay is even longer and its power margin thinner. But the successful test on Voyager 2 gives the team something they did not have before this month, confidence that the engineering works exactly as calculated across a gap of nearly a full day in each direction. And there's a second milestone converging on this exact same window of time, one that has nothing to do with power budgets and everything to do with pure, staggering distance. On November 18th, 2026, at 2:16 and 7 seconds in the morning Pacific Standard Time, Voyager 1 will reach a distance of precisely 16,194,799 to 96 miles from Earth. A distance so vast, it equals exactly one light day, the distance a beam of light covers in 24 full hours. No human-made object has ever reached that distance before, and none is expected to reach it again for a very long time after Voyager 1 eventually falls silent. Voyager 2, still trailing at roughly 13 billion miles out thanks to the longer four-planet route it took decades ago, is not far behind on the same outward trajectory, both spacecraft escaping the solar system in different directions at more than 3 astronomical units per year. Think about what that one light day distance actually means for the team still operating these machines. Send a command to Voyager 1 on a Monday, and you will not know whether it arrived until Tuesday. You will not receive the response until Wednesday. Every diagnostic exchange, every step of a procedure like the Big Bang costs a minimum of 2 full days just to complete one round of communication, and that gap will only keep growing as both spacecraft push outward at more than 35,000 miles an hour, carrying instruments that are quite literally becoming harder to reach with every second that passes. If you have made it this far, drop a comment and tell me honestly whether you had heard about Voyager 2's role in any of this before today, because public conversation around these two spacecraft focuses almost entirely on Voyager 1, and Voyager 2's contribution genuinely deserves more recognition than it usually gets. And if you know someone who would find this as fascinating as you clearly do, go ahead and share this with them, because stories like this tend to get buried under louder, less accurate headlines, and the real version deserves to travel just as far as the spacecraft itself. Now, here is where the deeper stakes of this story actually live, because none of this is simply about extending the operational life of an old machine for its own sake. Every additional month Voyager 2's instruments stay powered on is another month of genuinely irreplaceable data about a region of space humanity has almost no other way of directly studying. There is currently no funded mission anywhere in development capable of reaching interstellar space and repeating what these two spacecraft have already done. NASA and researchers at Johns Hopkins have spent years quietly developing concept studies for something called the Interstellar Probe, a purpose-built successor carrying modern instruments specifically engineered to characterize the heliopause in far greater detail than the repurposed 1970s hardware currently doing the job almost by accident. But that mission has not been funded, has not been built, and has not launched, and even under an optimistic timeline, it would take decades just to reach the same boundary Voyager 2 already crossed back in 2018. Every extra year of data these two aging machines manage to collect is quite literally irreplaceable for at least a generation, and possibly much longer than that. Consider everything that single plasma instrument on Voyager 2 gave scientists that they otherwise would not have had. Before its 2018 crossing, essentially everything researchers thought they understood about conditions in interstellar space came from indirect inference and theoretical modeling built on observations made from the safety of our own solar system. Voyager 2 turned that theoretical picture into a direct, measured reality, and in doing so revealed a boundary considerably messier, more permeable, and more dynamic than the clean textbook diagrams had ever suggested. The heliosphere that shields every planet, every moon, and every living thing in our solar system from the harsher radiation environment of interstellar space is not the simple sealed bubble most people imagine when they picture it. It leaks. It shifts. Its size does not track cleanly with solar activity the way models predicted. A mystery that, in Cremigas' own words, scientists still do not fully understand years after the data first came in. That matters beyond pure curiosity, because that same imperfect permeable shield is the only thing standing between the surface of our own planet and the full, undiluted force of galactic cosmic radiation, streaming in from the depths of stars that exploded long before our sun ever formed. Understanding exactly how that shield behaves, how it might change over the vastly longer stretches of geological time that actually matter for life on Earth, depends entirely on data that only these two aging, dying spacecraft are currently capable of providing. That is what is actually at stake every time engineers at JPL make one of these increasingly difficult calls about which system to save and which to sacrifice. It is not simply about extending the life of an old piece of hardware for sentimental reasons, although the sentiment is real and it is earned. It is about keeping open, for as long as physically possible, the only real-time window humanity currently has into a region of the universe no other instrument has ever directly sampled. When Voyager 2's last functioning instrument finally falls silent, whenever that day arrives, sometime in the early 2030s, if current power projections hold, that window will not pause. It will close completely, and it will likely stay closed for decades because nothing capable of replacing it currently exists or is funded to exist anytime soon. And when that silence comes, there will be no dramatic final transmission, no last message decoded triumphantly in a control room somewhere. The signal will simply, gradually, weaken past the point where even the most sensitive receiving dishes on Earth, the enormous radio antennas of NASA's deep space network spread across California, Spain, and Australia, so that one is always facing the right direction as the Earth rotates, can still pull it out of the background noise of the universe. And then, after nearly half a century of continuous contact, it will simply stop. But here is the part of this story that deserves to be the thing you carry with you after this video ends, because it changes the tone of everything that comes before it. Even after that eventual silence, Voyager 2 itself does not stop existing, and it does not stop moving. There is nothing in interstellar space to slow it down, no atmosphere to create drag, no gravitational pull strong enough to meaningfully bend its path. It will simply keep drifting outward in an almost perfectly straight line, carrying with it something bolted to its frame that will genuinely outlast every single person who ever worked on this mission, and very likely outlast the human species itself. Attached to Voyager 2, exactly as it is attached to Voyager 1, is the Golden Record, a phonograph disc plated in gold and curated by a committee led by the astronomer Carl Sagan back in 1977. Etched into its grooves are 90 minutes of music drawn from cultures scattered across the entire history of human civilization, spoken greetings recorded in 55 different human languages, natural sounds of Earth, thunder, wind, ocean waves, the calls of whales moving through deep water, and more than 100 images encoded directly into the recording, showing everything from basic human anatomy to city streets to the double helix structure of DNA, complete with playback instructions etched onto its cover in case whoever eventually finds it has no concept of what a record even is. Researchers studying both spacecraft's long-term trajectories estimate they will continue orbiting the center of the Milky Way for something in the range of 5 billion years or longer, essentially outlasting the sun and the solar system that built them, with odds of ever colliding with anything else out there sitting at almost precisely zero. One scientist who spent years working on the mission's plasma wave data was once asked, half seriously, what condition the spacecraft might be in after 5 billion years of drifting, and simply joked that they might look a little worn by then. So somewhere out there right now, more than 13 billion miles from your kitchen table, that spacecraft is still moving, still carrying that message, and for at least a little while longer, thanks to a maneuver nicknamed after the birth of the universe itself, it is still listening and still talking back. 3 fragile instruments, kept alive by a piece of decaying plutonium sealed into a metal canister nearly 50 years ago, running on less power than it takes to light the inside of your refrigerator, are still measuring the actual physical texture of the space between stars and sending that information home across a gap so vast that the answer to any single question takes the better part of 2 days just to arrive. The team that built this mission in the 1970s could not possibly have known it would still be delivering front-page discoveries in 2026. They planned for 5 years. They got nearly 50. And counting, thanks to careful engineering, a 176-year planetary alignment nobody will see again in this lifetime, and a small group of engineers at JPL who, every year, find one more clever way to squeeze a few more months of life out of a machine everyone, including its own designers, assumed would have gone silent decades ago. The clock is still running. The power is still dropping, 4 watts at a time, every year, with absolute mathematical certainty. But right now, in the summer of 2026, that clock just quietly bought itself another year, and somewhere out past the edge of everything the sun touches, a 50-year-old machine keeps drifting deeper into the dark, still sending its signal home, for as long as anyone here is still listening. If you want to know the moment engineers confirm the same fix on Voyager 1, and whether that long shutdown instrument ever comes back online, subscribe and turn on notifications, because that update is coming within the next few months. And when it lands, you will already understand exactly what you are looking at. Thanks for watching, and I will see you in the next one.